Hello, everyone, and welcome to our webinar, Measure More, Lock in Less, the Open Approach to MicroMet Data. My name is Aspen Nielsen. I'll be your host and moderator today. Joining me is Campbell Scientific's Director of Micrometeorology, Dr. Ben Conrad. Ben, how are you doing today?
Doing great, Aspen. How about yourself?
I'm doing well, thank you. Today, we will dive into the case for open architectures in Micromet station design. Please remain muted for the entire presentation. If at any point you have a question, please click on the Questions tab at the top of the screen and type your question in there. At the end of the meeting, we will review the questions. With that out of the way, let's get started. Ben, let's start by discussing proprietary or closed architecture designs. What challenges do you see with this framework?
Thanks, Aspen. So some of the problems that you have with proprietary systems, whether these are micromet systems or other general meteorological stations, is you can incur hidden costs. Sometimes they have lack of flexibility, and they can actually lead to innovation slowdowns. So let's explore each of these individually. The first one is hidden costs. If you have a proprietary system, especially in a micromet station, you can run into issues with single vendor calibration standards, communication protocols, and data management systems. While some of the more specialized parts of an eddy covariance system, such as a sonic anemometer or a gas analyzer, may be so specialized that it can only go back to the vendor that manufactured it, there are other components on that station that you want to be able to possibly send to a calibration house that's a little bit closer to where you are deploying your station. If you have to send everything back to a single vendor for calibration, you can run into issues where you have significant gaps in data. You also don't want to be locked in to single vendor communication protocols. If you are, you can run into cases where that system may not be able to communicate with other sensors that you may want to try out in the future. Also, data management systems, if they're locked into a single vendor, it doesn't provide you with the flexibility to try out new management systems that may actually work better for you. Another hidden cost could be that you get locked into a single vendor pricing strategy. And once you're locked into that strategy or that single vendor pricing, it's difficult to switch to another offering. So while at first it may seem like really good value, if that vendor or if that proprietary system goes up in price year after year and eventually comes out of range of your budget, you may have to switch altogether to a different offering, and that's very difficult to do. Another hidden cost is if you find yourself wanting to add additional measurements, you may actually have to buy additional add-ons if your proprietary system isn't open enough to allow third-party sensors to interact with it. So that's an incurred cost that you may not have planned for in the beginning because perhaps you didn't know that you were going to need some additional measurements, or perhaps some new technology becomes available that you want to be able to interface it with your eddy covariance system. And if you can't do that natively, you have to perhaps add in additional add-ons. You may not have full sovereignty over data if provider controls the database, the dashboard, or the API. So as long as you're a paying customer to this vendor, for example, if you're in a cloud-based subscription, certainly you would have access to your data. However, in some cases, once you stop paying for that software service or that cloud-based service, you could lose access to all of your historical data if you hadn't downloaded it previously. Or perhaps there's not even an option to download it, and there's only an option to view what they have in the cloud. Another hidden cost or issue with proprietary systems is that lack of integration flexibility. So you have limited ability to interface new sensing technologies as measurement needs change. So as you go through your research and you recognize that, maybe there's a different sensing technology out there that you want to try out to answer one of your important research questions. If you can't integrate that into your proprietary system, obviously that hinders your research. Additionally, limited ability to mix and match best-in-class instrument offerings. It's rare that you would find a vendor that every single offering they have is best in class. If you've got 15, 20 sensors, certainly they could produce really good instrumentation, but there's always somebody pushing the technology envelope, and you want to be able to mix and match best in class. Additionally, you want to be able to evaluate sensors, and so maybe you don't need the super high-end temp RH sensor, for example, and one of the middle grade ones will work well for you. If you can't integrate that seamlessly into your system, it becomes a challenge to even make that decision. So I have on the left-hand side there just a couple examples of a HygroView 10 versus a HygroView 5. Maybe a HygroView 5 is good enough for you and it is more economical and fits into your budget better. But if all we ever offered was just a HygroView 10, you wouldn't have that ability to go for perhaps what fits your station better. Same thing with a barometer, a BaraView 10 versus our CS 100 or 106. You need to make those evaluations as well. And the lack of having an integration flexibility limits you very much in being able to make those decisions. Also, proprietary data formats, those increase complexity for using open source software packages. There's new algorithms coming out. Eddy covariance is very much still an active area of research. And so if you have the data formats that are proprietary, it's really hard to go out and use those new tools that are possibly being written in other programming languages like R or Python maybe. You want to make sure your data formats are open so that you can use them in the open software space. Finally, scaling to new environments may be difficult. What's good out on Mount Aconcagua may not be what you need for an alfalfa field. So you need to be able to scale back and forth between those environments. Otherwise, you end up having to rebuy stations. So the ability to move one station from, for example, an alfalfa field up to a mountain, that's not really an option if you have a lack of integration and flexibility. Innovation slowdowns is another one that we like to discuss. The roadmap of the provider of that proprietary system may actually be different than what you need, and that can slow down your scientific and technical progress. So you can see here just some examples. There's new AI coming out all the time and how that affects your eddy covariance processing. There's new post hoc methods for processing or reprocessing high frequency data. If you don't have the ability to do that, you're slowed down on innovation. Additionally, if you wanted to add perhaps a new trace gas sensor to your system, a new eddy covariance trace gas sensor, if you're locked into a proprietary system and the roadmap of that proprietary system owner doesn't include a new trace gas system, well, you may not be able to do it. You may have to switch out your entire system to get into a more open platform. Finally, community collaboration can actually become stifled if new ideas cannot be implemented into a closed black box system. Again, kind of going back into this idea of if there are new algorithms coming out, but yet you're unable to really implement those into your data processing workflow, that can become an issue and new ideas essentially become stifled.
So Ben, what is the solution to all of this?
So there's one of the solutions that you can use when designing your eddy covariance system is to look for flexible, non-proprietary solutions. And this really becomes powerful because it leads to sensor agnosticism. It helps you with future proofing, data transparency, and long-term value. So I'm going to go through each one of these as well. The first one being that sensor agnosticism. I've hinted at this one a little bit already. But at Campbell Scientific, our systems are based on an open platform data logger that allows for integration of third-party sensors. The reason that this is so powerful is because it allows for flexibility across projects, and you get to mix and match hardware to specific environments or research needs. Again, what may be good for an alfalfa field is not necessarily going to work well up on Mount Aconcagua. You get a benefit to your budget because the best fit sensor can be purchased at the best price rather than a price that is set by a single vendor. It also allows for cross comparison between multiple sensors measuring the same variable. For those that have been working with eddy covariance for a number of years, you probably are using a temperature RH sensor like an HMP 155A from Vaisala. However, new temp RH sensors have come out onto the market in recent years. And instead of just trusting that those new ones are just as good as your HMP 155A, the ability to go ahead and add that new sensor to your system and actually do a direct comparison between the two is extremely powerful and helps you make a decision rather than always just trusting the word of others or following in line with what everybody else is doing. What really allows this is, again, that open platform data logger and the CR basic programming language that goes with it. That allows us to interface with virtually any sensor out there on the market for meteorological or eddy covariance measurements. Future-proofing is also extremely important. These systems are not cheap. We all know that there could be upwards of 50,000 plus USD to purchase an eddy covariance system. Our systems are designed around expansion, and this helps to ensure that they can keep up with technological advances so you don't have to scrap everything once new things come out. So you have the ability to swap in new sensors as they become available to the market that are not tied to a single vendor. You have easier integration of emerging technology such as edge computing, low power wireless, or onboard analytics. Something as simple as a charge regulator that can help you determine the battery state or power state of your system becomes incredibly powerful when you allow for those onboard analytics from that charge regulator to come into your system. Future-proofing also comes into play with support for community data standards. Those change over time as new research unveils new thoughts and ideas. The system supports single sensor swaps that allow for longer field deployments. So if something happens to your sonic or something happens to your gas analyzer, you can swap those out with our open architecture. This is really powerful for those that have cases where data continuity is critical and something catastrophic happens to their system. They can borrow or lend a system from an entity like Ameriflux, and our data logger allows them to easily integrate that. Data transparency is critical. Our systems are designed around transparency where the raw data is always provided. Now, why is that important? Because you need the ability to reprocess data. Even if you don't ever do it, the fact that you can archive that data, and if something comes up in that you recognize later on, you can go back and reprocess. Additionally, updated algorithms can be applied as the scientific standards evolve. Our data are always provided in non-proprietary formats, which are widely accepted. And again, this allows for work with your peers. You get allows for peer validation, where anomalies or biases can be spotted more readily than them trying to read in proprietary data. Another example of how we take data transparency and where that raw data and the ability to reprocess becomes very powerful is actually a very recent example where the AGU held a Chapman Energy Balance Conference just a couple weeks ago. And during that conference, it sounded like there was quite a bit of interest around transducer shadowing and how that affects the energy balance in the form of how that affects those fluxes. One of the things that manufacturers tend to do is apply corrections in a black box manner. So there may be shadowing corrections being applied to your 3D sonic anemometer that you may or may not need, or may not want, or may not be aware of. At Campbell Scientific, we provide our sonic with an option to turn on or off those shadow corrections. And with that raw data, you can always go back and process it either way. So, for example, if you leave your shadow correction, or if you turn your shadow correction on, you're going to get wind speeds that have the shadow correction applied. You can then use an algorithm to undo those shadow corrections on the raw data to see what the effect is, or go the other way. But the power of having that raw data is critical in giving you the choice of whether you want to apply a shadow correction or not. Long-term value. I mentioned that these systems are not cheap. They are very expensive. And so you want to get the most value out of them that you can. We provide systems for long-term value that ensures data are usable, credible, and adaptable. Again, we always have that ability to archive raw high-frequency data. And why does that contribute to long-term value? Because by archiving that data, researchers can come back years and years later and reprocess it with new algorithms or push that data into new models. So the life of that data is not limited to the 3 to 5 year grant that you initially purchased it for. Your system remains adaptable even as technologies shift. As vendors come out with new gas analyzers, new sonic anemometers, new temperature sensors, RH sensors, etc., our system is adaptable and allows you to interface with those. We don't have a required license or service contract or expensive upgrades. Our systems are built for you to be able to choose when you're ready to upgrade. And if you choose to have service contracts, that's fine, but we're not forcing you into them. Finally, that legacy data is critical for integrating cleanly with global syntheses and giving insight not just to perhaps your field site, but to field sites across the globe. So how do you evaluate your station for flexibility? These are just some of the things that I think are important when you're looking at non-proprietary EC systems that'll help ensure long-term value and success. What you want to do is look for the following. You want to make sure that the system that you're using or purchasing has sensor compatibility and modularity. In other words, you want to be able to choose whether you have an open path or a closed path eddy covariance system, whether you have 3D sonic from Campbell Scientific or whether you use 3D sonics from third parties, and the ability to get biomet sensors from a variety of manufacturers. You want to always have open data and processing standards that allow for widely accepted data formats, compatibility with open source data processing packages, and clear documentation and access for flux computation algorithms. While companies today provide you with 30-minute fully corrected fluxes, those have to be documented and you have to have access to them. Without the access, it's really hard to go back and reprocess in the same way that the manufacturer did originally. The open data is critical in this community, especially where we share data. FluxNet is a great example of a database where researchers worldwide are contributing to the database so that that data can be shared amongst researchers and used more widely. Data synchronization between gas and wind components is also critical. I put this here because I keep talking about the ability to mix and match on a Campbell Scientific station. It doesn't come without considerations, however, especially when you're talking about eddy covariance. You need to make sure that you can synchronize fully your gas and wind components. Also, you want rugged, low power, and field serviceable. Having flexible stations that are not rugged, not low power, and not field serviceable aren't going to get you very far. Finally, again, coming back to that data sharing, we need to be able to use the data from these stations and we need to make sure they're compatible with global flux networks and future-proofed against sensor obsolescence.
Thank you for sharing, Ben. Now, before we let you all go, let's take a look at the questions from our audience. Looks like we've got a couple. The first one is, are there any challenges with an open architecture or benefits to a closed architecture?
Thanks for that question. It is a really good question. And if there wasn't a benefit for closed architecture or proprietary, they would never exist. But one of the biggest benefits of those is your ease of use. So if you're not technically trained to work with eddy covariance systems or you have very little experience, maybe you're just an operational flux user, certainly using these more closed systems will allow you to get up and running more quickly. However, you may find yourself in the future wishing it was more open, because the open platform advantages really are that ability to change with the times. As new technology comes out, you can implement that into your system. But with it, obviously it comes a little bit more complex user experience, as you have to interact with the CR basic language, or you need to contract somebody from Campbell Scientific or others to write that code for you.
Excellent, thank you. How difficult is it to measure new variables and add to the existing system?
It's highly dependent on what type of sensor you're interfacing with. For example, if you are if you are interfacing with, for example, an SDI-12 digital sensor, those are fairly easy to program in our data loggers. Typically, the hardest part about those is making sure you have the SDI-12 addresses correct in the data logger and in the sensor. But digital sensors typically are fairly easy to interface with. Perhaps some other digital sensors that are RS-485, that include serial strings, those become a little bit more complex to interface into our system. But again, we're always here for help, available to help you through that. Analog sensors are fairly easy as well, as long as you understand the voltage ranges and how to convert from engineering units into scientific units. Those typically aren't very difficult.
Thank you for sharing. And with that, we will end the webinar. Thank you for joining us today as we explore the benefits of open platform MicroMet architectures. Until next time, Campbell Scientific, for when measurements matter. Thank you.
Thank you.